Welcome back to the Networking Mastery Curriculum. This is Stage 1, Lesson 3. Today, we're tackling one of the most important ideas in all of networking, encapsulation. By the end of this lesson, you'll understand exactly what each layer of the stack wraps around your data as it's sent, and how the receiving side unwraps it piece by piece to recover the original message. Here's the roadmap for the next few minutes. First, we'll build up the idea of encapsulation, how each layer wraps your data with its own header as it travels down the stack. Then we'll reverse the process and look at de-encapsulation, where the receiver peels those headers off one by one. After that, we'll name the data unit at each layer, what we call a segment, a packet, a frame, and so on. And finally, we'll put it all together by reading a real packet capture through the same mental model. Let's start by watching data descend the stack. At the top, your application produces a message, say an HTTP request like get index.html. Transport wraps it in a TCP header, turning it into a segment. Network adds an IP header, making it a packet. Data link surrounds that with an Ethernet header and trailer to form a frame, and finally, the physical layer pushes it out as raw bits on the wire. Each step adds its own header, so the data quite literally grows as it travels down. And those names we just used aren't interchangeable. Each layer has its own term called the Protocol Data Unit, or PDU. At the application layer, it's simply data or a message. Transport calls it a segment for TCP or a datagram for UDP. Network produces a packet. Data link produces a frame. And the physical layer deals in raw bits. This matters in practice. When an engineer says frames are being dropped, they're pointing at layer 2, while dropped packets usually means a layer 3 issue. Now, every one of those wrappers we keep adding has a real cost in bytes. Ethernet contributes 14 bytes plus a 4-byte frame check sequence. IPv4 adds another 20. IPv6 a fixed 40. TCP another 20, while UDP keeps things lean at just 8. And if you're running HTTPS, TLS layers on another 20 to 40 bytes per record. Add up a typical TCP over IPv4 stack, and you're spending 54 bytes on headers before a single byte of application data. So with a standard 1500 byte MTU, your actual payload is closer to 1446 bytes, a small but constant tax for all that encapsulation. Now let's flip the process around and watch what happens on the receiving end. The bits arrive at layer 1 as raw electrical or optical signals, and from there, each layer peels back its own wrapper in reverse order. Layer 2 checks the destination MAC and strips the Ethernet frame. Layer 3 confirms the IP address belongs to this host and removes the IP header. Layer 4 reads the TCP port to know which application gets the payload. And finally, Layer 7 receives the clean request. In this case, a simple HTTP GET. Examine, strip, pass up. That's the rhythm of de-encapsulation. But here's an important detail about that journey. The routers in between don't unwrap everything. A router only climbs up to Layer 3. It reads the Ethernet header to accept the frame, strips it, looks at the IP header to decide where the packet goes next, decrements the TTL, then builds a fresh Ethernet header for the next hop. It never peeks at TCP ports or application data. Those layers stay sealed until the packet reaches its final destination. Specialized boxes like NAT devices or next-gen firewalls are the exceptions, but a plain router stops at L3. Now let's see all of this in a real tool. When you open a capture in Wireshark, the layers we've been describing show up as nested sections you can expand. The Ethernet frame on the outside, the IPv4 packet inside it, and the TCP segment tucked in the middle. At the link layer, you see the MAC addresses of just this hop. One layer in, IPv4 shows the true end-to-end addresses, the TTL counting down, and a protocol field pointing at TCP. And finally, TCP reveals the ports and flags. Here, a SYN, which means we're catching the very first step of a handshake. So why does all this layering actually matter? Because every device on the path only looks at the layers it cares about. A router checking MTU works at L3, so a lower MTU link downstream forces fragmentation or drops. A firewall rule like block TCP port 22 only needs to peak at the L4 header. An L4 load balancer hashes on source IP and port, while an L7 balancer reads deeper to find the HTTP host header. TLS encrypts everything from L5 up, but routers still see L3 and L4 just fine. And a VPN, it wraps the whole packet inside another packet, encapsulation nested inside encapsulation. That last point about TLS deserves a closer look, because it's where a lot of people get confused about privacy. Think of it as an encryption boundary that cuts right across the stack. Everything from layer 5 up, your HTTP request, cookies, form data, the response body gets sealed inside TLS, but layers 3 and 4 stay in the clear because routers need them to do their job. So even with HTTPS, your ISP still sees that you talk to 142.250 190.46 on port 443. The contents are private. The conversation itself is not. A VPN takes that same idea even further by wrapping the whole packet, headers and all, inside another packet. Your client builds the normal Ethernet, IP, TCP, and data stack you'd expect, then encapsulates the entire thing behind a fresh VPN header, like IPsec ESP, and a brand new outer IP header pointing at the VPN gateway. So from the internet's perspective, you're only ever talking to that gateway. The real destination is tucked away inside, hidden until the gateway strips the outer wrapping and forwards the inner packet on. It's encapsulation layered on top of encapsulation. So let's lock in what matters from this lesson. Encapsulation means each layer wraps the data with its own header on the way down, and de-encapsulation reverses that on the way up. Mind your vocabulary. Data becomes a segment, then a packet, then a frame, and finally bits on the wire. Remember the numbers too. Standard TCP over IPv4 costs you 54 bytes of overhead, leaving 1446 bytes of payload inside a 1500 byte MTU. And keep in mind that pure routers work at layers 1 through 3, while NAT devices and firewalls have to peek deeper into layer 4 and beyond. Keep this cheat sheet handy as your quick reference. It captures the entire lesson at a glance. The two columns map every PDU name to its layer, lock in the overhead math, and remind you which devices operate where in the stack. And one practical tip: when you open Wireshark, you'll see these same layers as expandable sections in every captured frame, mirroring the encapsulation model exactly. That's your bridge from theory to hands-on practice. And that wraps up Lesson 3. Coming up next in Lesson 4, we'll tackle MTU, MSS, and fragmentation, the rules that govern how big your packets can actually be and what happens when they don't fit. You'll see why packet size quietly causes some of the trickiest networking issues out there. Until then, visit Dargslan.com or find us on YouTube for the full series. See you in the next lesson.